Hello again, and thank you for joining us on a Q&A edition of Space Nuts. Andrew Dunkley here. Thanks for your company. Today, we got 4 questions to answer. Actually, that usually ends up being 10 because people ask multiple questions. I suppose you've got to use your time wisely. But we've got a question about the journey of comets. We've got a question about magnetic pole reversal. We've had that one before, but it was quite a while back. It's worth revisiting. The origin of time has been brought up, and the age of the universe versus galaxies far, far away. We'll tackle all of that on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining us to unpack all of that is Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. Nice to see you again.
Good to see you too. Haven't changed much since I last laid eyes on you.
It's funny you should say that. Neither have you.
Looking good. Let's do some questions, shall we?
Why not? Ross Blow here, so we might as well.
Yes, and nice to get a couple of new voices on the audio question list. And of course, if you do have questions for us, jump on our website and send them through. Just click on the Ask Me Anything button, AMA, up the top, or it's more of a link. And if you've got a device with a microphone, you should be able to record. Although a few people have had issues with it lately, so maybe that's the reason why we're short of questions. But anyway, we've got a couple. This first one comes from Andrea.
Hi, Andrew and Fred. This is Andrea from Wanneroo in Perth, Western Australia. My question is around comets again, and how is their path created and tracked like their elliptical path? Do they all follow a similar journey, or do they create their own as they come through? Thanks heaps. Appreciate it, and love the show.
Thanks, Andrea. Lovely to hear from you, and nice to get a new voice into the program. And Wanneroo, I think that's an Aboriginal word for wanting a pet kangaroo. No?
I wouldn't have gone there.
Couldn't help myself. So Andrea's question is all about the journey of comets. Do they kind of all do the same thing, or do they figure it out for themselves, or are they, they're real loners and don't want to do what everyone else is doing?
So, like I said, it is a great question, Andrea, and it's actually got a little bit more to it than perhaps people might think, because comets, as you know, they make their appearance from time to time, an individual comet, some of them fairly regularly. But the story starts much, much further away from the sun than any of the planets, way, way beyond the trans-Neptunian objects, those icy asteroids out there, where we've got this hypothesized, never yet observed, but well established, I think is the best way to call it, shell of cometary debris. And by that, I mean chunks of ice, basically, which are the leftovers from the gas cloud from which the solar system formed. So these are ancient blocks of dusty ice.
Let's be realistic. It's where the tradies left their junk after they finished building the solar system.
That's right.
That's what it is.
All right. Yeah. Well, the hypothesized celestial tradies, it's the debris.
Yes.
It's the leftover stuff, frozen at very low temperatures with a dusty contents as well. So the thinking is that shell of comets, when our sun, as it trundles its way around the galaxy, it passes nearby other stars and other objects, which gravitationally disturb the Oort Cloud. And so from time to time, you might get quite large numbers of these cometary bodies being disturbed from where they lie and plunging down into the inner solar system. So there's probably a steady flux of these things coming in, But once in a while, because of gravitational disturbances, you'll get a lot more. And that was actually the subject of a book written by two colleagues of mine in Edinburgh called The Cosmic Serpent, when they worked out that maybe comets had actually had a lot to do with shaping the Earth, but impact from comets when the sun passed another star. Anyway, here we have comets. So here's a Mr. Comet sitting out there in the, I beg your pardon, Ms. Comet sitting out there in the Oort Cloud, and falls in towards the inner solar system in a path that is almost a straight line, but it's not, because it is actually an ellipse. Anything that follows the gravity of an object follows in an elliptical path. It's in an orbit that often takes it round the sun, and so you get that's when the sun's radiation starts acting on the ice and you start to see it. So that path is determined just by gravity and the gravitational mechanics, and sort of determined what the starting point of that comet is in the Oort Cloud. Often, though, there might be an interaction with the gravity of some of the planets in the inner solar system, most especially Jupiter. And we think that many comets have their orbits modified by the planet Jupiter, so they become much, much shorter, because in an orbit to take you out to the Oort Cloud, you're talking about tens, maybe even hundreds of thousands of years. But we find comets with periods much shorter than that, some even as small as 4 or 5 years. Anything with a period of revolution around the sun of less than 200 years is called a short period comet, and that includes Comet Halley, 76 years. So that came down from the Oort Cloud a long, long time ago. It interacted with Jupiter. That pushed it into a short period orbit. So their paths are being modified all the time by interactions with the planets, and sometimes they're modified in a really quite serious way. It's a great question, Andrea, and quite nice to think of it in the terms that you put it. What determines the paths that these objects take? It's all about gravity and where they started off from, and whether they've interacted with planets on the way down.
You did mention the Oort Cloud. They also come from the Kuiper Belt, don't they?
The Kuiper Belts are much nearer than the Oort Cloud. And there are one or two objects, because the Kuiper Belt, they're pretty icy out there as well. But there might be rocky objects with a coating of ice, a bit like we think Pluto is. Rocky core, slushy ocean over the top, icy crust. Whereas the comets don't have crusts, they're just chunks of ice. And I might mention the Oort Cloud was postulated by a very well-known Dutch astronomer, Jan Oort. I think in the 1950s was when he said comets must come from a sort of reservoir somewhere, a cloud of comets. And the reason why he postulated that it was spherical, a spherical shell, is that comets, when they come in from the Oort Cloud, come in at all different angles. They don't just sit in the plane of the solar system.
Yeah. Well, we haven't seen it, though, have we, the Oort Cloud? No, we haven't. So it's still theoretical, or we've got enough evidence to know that it's there, like Planet 9?
I think there's more evidence for comets, for Oort Cloud, than for Planet 9.
Yeah.
You're right, though. I mean, the problem is these objects are small. They're typically a few kilometers across, and they're at they're at almost a light year away is the distance of the Oort Cloud. It's a long, long way out. It's way, way beyond where Voyager 1 is now, at 23 light hours away. It's much, much further than that. And so you're not ever going to be able to see individual objects in the Oort Cloud with our telescopes, but the inferences and all the evidence supports the existence of this cloud.
Okay. Thank you, Andrea. Fabulous question. And we learn a little bit more about comets. Our next question comes from Michael in Canada. Apologies, Fred and Andrew. I do not have a dark matter or black hole question at this time, but perhaps this question still might be acceptable. I understand that Earth is somewhat overdue for a magnetic pole reversal, and that this is also not something immediate when it does occur. How likely is it that there might be some extraordinary negative effects on satellites in low Earth orbit? Thank you, Fred and Andrew, and thank you, Hugh, in the studio, for keeping these two in line every show. Yes, yes. He's conspicuous by his absence, is Hugh. Very busy man, though. Let's see. All right. Negative effect on satellites in low Earth orbit if we start seeing that magnetic pole reversal. I suppose we should address the fact that it doesn't just happen like a light switch.
That's certainly true, yes. So the evidence for pole reversals, they probably have to rehearse it as well, but the evidence for magnetic pole reversal comes from what we know from principally rocks deep under the ocean bed rocks, which have the grains of silicates, they're aligned in a way that you can trace the Earth's magnetic history. And so the thinking is, I think this is still the sort of number that people talk about, something like 3 reversals of the Earth's magnetism every million years. Now, that's fairly slow compared with an object like the sun, which we think reverses its magnetic poles every 22 years. So that's, that polar reversal, which we can sense from looking at sunspots, is much faster. So the process seems to be on Earth that you've got a gradual weakening of the magnetic field, which when it reappears is the other way around. And we think it's due to the interaction between the Earth's 2 cores. We've got a solid metallic core with a liquid metallic core on the outside, and the 2 are rotating with respect to one another. So it's a dynamo effect, which generates a magnetic field. So we're talking about timescales for the reversal of thousands of years. It's not something, as you said, it doesn't switch on overnight. The process takes a long, long time. Yeah. And there will be some spacecraft that will last for thousands of years because they're high enough that their orbits are not threatened by decay. However, I think the effects of the reversal of magnetic polarity are going to be negligible compared with the magnetic effects that you get from the sun's the solar wind and the stream of subatomic particles that comes from the sun. I think that's the dominant magnetic force for satellites. They're beyond the protective magnetosphere that the Earth provides. That reversal will produce a reduction in the magnetosphere, and that itself might allow spacecraft to be bombarded more by solar wind particles. So there could be an effect caused by the weakening of the Earth's magnetic field as the polar reversal takes place.
Okay, so there is something to that.
Yeah, I think
issue.
You're probably right. Yeah,
because one of the big dangers we face these days is a direct hit from a coronal mass ejection that could affect our electronics.
Yeah, fries the electronics.
Fries the electronics, and I know emergency services in this country and probably in other parts of the world are building that scenario into their emergency response systems. It's unpredictable. I mean, it could happen. It may never happen, but it has happened in the past. In the early years of the telegraph, there was one particular case where the system was suffered a direct hit, and no one knew what was going on. It was just a real shock.
One person did, and that was an astronomer called Carrington. I can't remember.
That's right, the Carrington event.
Yeah, I can't remember his first name. His picture's actually on the current issue of Astronomy and Geophysics, which is the Royal Astronomical Society's journal. And there's a picture on the front of it. I haven't read it yet, but it's Meet Mr. Carrington is the title of the article.
Right. I'm just trying to look up his name. Richard Carrington.
Carrington, yes.
And
so he observed. Sorry, I was going to say he observed a very bright flare on the sun, and then that was followed by all these magnetic effects that you've spoken about. So he recorded that flare.
Yeah, September the 1st, 1859 it was.
Yep.
the Carrington event. So yes, Michael, definitely something to your concerns. Hopefully never, but they can't write off the possibility. Thanks for your question. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson. Let's take a little break from the show to tell you about our sponsor, Incogni. And if you've ever had your information harvested from the World Wide Web, this is the tool for you. Of course, your information is easily available online. We're talking personal information. We're talking addresses, phone numbers, email addresses, even bank details if your protection isn't good enough. This stuff gets harvested and it is sold by data brokers. They sell it to other people who then scam you or other people in your name, which is happening a lot. So what is the solution? Well, the solution is you can go online and clear out your personal data by yourself if you've got a couple of years up your sleeve, because that's how long it will take you. Or you can use a ready-made solution, and that is Incogni. And as a Space Nuts listener, you get a special deal with Incogni at the moment. It is simple. It works in the background. It provides ongoing protection, so you can sit back, relax, and know that Incogni is protecting you from these harvesters and scammers. And all you have to do is create an account, give Incogni permission to work on your behalf, and that's it. Job done. And if you want to check out the pricing, there's a 60% off deal for Space Nuts listeners at the moment. That is fantastic. Just go to incogni.com/spacenuts for more information. That's incogni.com/spacenuts and see what works for you. But peace of mind is probably, something that we all need in this world of data thieves. So check it out today, incogni.com/spacenuts.
I believe that this nation should commit itself to achieving the goal before this decade is out of landing a man on the moon and returning him safely to the earth.
Space Nuts.
Next question, Fred, comes from a local in Dubbo, New South Wales. Hello, George. I'm not sure if we've met. I hope we do someday if we haven't already, if that makes any sense at all. I have a question about the origin of time. Years ago, I read that time emanates from the ceaseless and never-ending motion of energy that pervades the entire universe. That's beautifully written, George. If this universal energy were to freeze or even disappear, would time as we know it still exist? Or would it be in a state of quintessence or maybe even disappear as well? It seems to me that without the motion of energy to bring forth time, there would be no time. The most interesting conundrum, don't you think? Thank you for the interesting podcasts. Thank you, George. Great to hear from a local. Yes, this is something we've talked about time and time again. Fred?
Look, it's a very deep thinking local as well, because George is pretty well on the money. I think what you read about a long time ago might not be current thought in this field, but time is one of the biggest mysteries that we have, and we really don't understand it, how it arises. We know it's a dimension. We know that in the relativity world, time is flexible. We know it bends. But when you look at quantum mechanics, it apparently doesn't exist. So it's a very, very peculiar thing. And that's one of the reasons why the two theories, the theory of relativity and quantum mechanics, why they're at loggerheads, because they've got fundamental inconsistencies between them. Now, I've tried to follow this argument and debate. It's taking place at a level of quantum mathematics that is far deeper than my capabilities from my fairly what's the word, tawdry degree in mathematics that I have, which I only just scraped through.
It's a better degree in mathematics than mine.
Well, anyway, yes, it nearly wasn't a degree at all. Only the generosity of the Scottish education system let me fail an exam 5 times and pass it on the 6th attempt. Yes.
Sounds like my driver's license.
All right. Okay. Don't remind me never to come driving with you. Anyway,
Hang of it eventually.
yeah. So the mathematics that, the quantum, particularly quantum mechanics or quantum theory people, theoreticians, that's the word I'm looking for. The mathematics that they use are very, very abstruse and obscure to the likes of me. I could probably use the words like Hilbert space and things like that, but that's all. Now, what I read, though, is really interesting. That it was actually Einstein who said time's an illusion. In fact, the quote comes from a letter he wrote to the widow of a close friend of his who died. And what he said in that letter was, to those of us who believe in physics, we know that the concepts of past, present, and future are only a stubbornly persistent illusion. And he said that because relativity suggests that all of time exists, that it's all there, and we see it as an illusion. We see it stepping from one moment to the next. But actually what we're doing is we're just ploughing through something that exists in its entirety, which sort of casts all sorts of interesting questions about free will and things of that sort. If what's going to happen is already predetermined, what happened to free will? But quantum physics. So I think the quantum theoreticians, they don't need time at all in their deliberations. And so what's, I think, emerging from this is that you've got these two different theories that suggest, and this is the language that they're using, that time actually doesn't exist, that time simply does not exist. And what we see as time actually emerges from quantum entanglement. Now, you and I have talked about quantum entanglement a lot because it's something that Space Nuts listeners like talking about, and I do too, even though it's not that straightforward to understand. But it's basically how you can, if you've got two quantum particles in a state of superposition, which means that you things like their position and their state are not determined until you observe them. If you've got two particles that come together in this entangled means, then they retain this, what Einstein called spooky connection at a distance. They retain that in some weird way. How time might emerge from that, or the illusion of time might emerge from that, I have no idea. But it is something that is very much ongoing, new physics ideas. Now, how do you probe that? How do you find out if these ideas are anything like the truth? Well, it's by looking for holes in relativity, for example. We test relativity all the time. It's good to, I think the last time I read about it was something like 1 part in 10 to the power 18 is how accurate it is. So it's a very, very robust theory.
Yeah.
But if you could
they keep trying to break it, but they can't find a hole in it yet.
If you could break it, then you might see a chink into the new physics that might underlie what we're talking about now. And likewise with the subatomic particle world, where we're seeing in the Large Hadron Collider, we are seeing new particles. A new one was discovered not that long ago, but it's one that is not sort of revealing any cracks in our understanding of the particle world. Supersymmetry was the buzzword 10 years ago, where people were hoping that the upgraded Large Hadron Collider would reveal evidence of what's called supersymmetry, which might talk about new dimensions and things of that sort, but there's absolutely no sign of it at the moment. So all of that's ongoing. Maybe there will be some chinks that appear. I hope when they do, you and I'll talk about it, Andrew.
Wouldn't that be cool? Yeah. I suppose you could, quite often when we talk about this sort of thing, people get together on the Space Nuts podcast group on Facebook and talk about time, and some will just say, look, time's a construct. It's not real. And I suppose to a certain degree that's true. We did invent time to suit ourselves on this planet. The construction of various forms of calendar and clocks, but we worked it in with what the planet's doing. That's our version of time, but we're talking about time at a universal level and the progression of existence, I suppose, for want of a better description.
I mean, yeah. I mean, to an astrophysicist, time seems to be a fundamental part of the universe because we see things evolving.
Yeah,
it's one of the reasons why the Big Bang Theory really rose to prominence. The fact that when you look further out into space, you're looking further back in time, and you see galaxies that are clearly different from what they are now. You're seeing them in the early universe. And of course, that is ongoing with the Webb telescope and all the weird and wonderful things we're discovering with that. So time is sort of real in that sense, but in a fundamental physics sense, maybe there's a deeper reality that hides underneath quantum theory and relativity. And it's down there where time is made.
Wow. Yeah, it's pretty deep stuff. I find it fascinating, even though I don't understand it at an intellectual level. I just know that when I look at my GPS on the golf course, it tells me I'm behind time because I'm playing too slow. That's about as deep as it gets for me. Thank you, George. Gee, I love that question. I hope we hear from you again, and I hope I run into you somewhere in Dubbo. Please say hello. Our final question comes from Tom.
Hi, this is Tom from Ireland. Love your show. Something I can't get my head around. I hope you can help. If I stand on the Earth and I have a powerful enough telescope and I can see, say, a galaxy that's 13 billion light years away. Now, if I turn my head and look 180 degrees in the opposite direction with the same telescope and I pick out a galaxy that's also 13 billion light years away, how can those two galaxies be 26 billion light years apart when the universe is only 13.8 billion years old? I ask this question because if I get it right, if I'm assuming right, when I see the galaxy that's 13.8 or 13 billion light years away, I'm seeing it as it was in that position 13 billion years ago. And likewise, the one in the opposite direction, I'm seeing it as it was 13 billion years ago. So how could both of them be that far apart with the universe only 13.8 billion years old? I know I'm missing something I just can't get my head around. Thank you. Love the show.
Thank you, Tom. This old chestnut, Fred, this old chestnut. It's come up once or twice over the years. But
He's put it very, very beautifully, though.
He has, hasn't he? Yes.
Very well, yeah.
Now, what's the solution?
Well, so I think the first thing to understand is that the universe is, we think it's 13.8 billion years old. So that's right, as exactly as Tom says, since the Big Bang. But immediately after the Big Bang, we hypothesize, and there's good evidence for this, that the universe went through a period of what we call inflation, where it expanded from the size of a football to the size of a galaxy in something like a gazillionth of a second.
Yeah.
It was something you can't get your head around.
Yeah, it's unimaginable, isn't it?
Yes, so expanding much faster than the speed of light. But as we've said before, the universe can actually do anything. It's not limited by the speed limit, which we are when we travel through the universe. When we travel through space, we're limited to the speed of light. But space itself can, and indeed did, expand at a very, very rapid rate. So what we have is a universe that is much, much bigger than what we can see. And that sort of explains, I think, the issue, because we, from our vantage point here on Earth, when we look out into space, we can only see so far back. And that is because we eventually, at great distance, we run into the flash of the Big Bang. You're looking so far back in time that you're still seeing the universe when it was a bright fog, which was not transparent. So it was this fog of radiation. And we see that as the cosmic microwave background radiation, which we've talked about many times. It's all over the sky. It's got slight variations in it, which correspond to temperature variations because of acoustic oscillations in the Big Bang. In other words, the noise of the Big Bang. So that's a horizon. Now, we can't see beyond that, Tom, but the universe itself goes on. It's almost as though we're in a bubble, in a huge universe, and all we can see is limited by that time of 13.8 billion years, because eventually we run into the flash of the Big Bang, looking back in time. Yeah. But because of the inflationary period, the hypervelocity expansion that the universe went through early in its history, then it is much, much bigger. So so you see a galaxy that's 13.8 billion years ago away, and then imagine yourself standing on that galaxy. You wouldn't see the galaxy that was 26 billion light years away, because you're limited by the horizon, the same horizon. From any point in the universe, you can only see back 13.8 billion years to the flash of the Big Bang. But the universe itself is much bigger. It's a difficult thing to get your head around, and Tom's conundrum is absolutely understandable, but that's the answer. The universe is a lot bigger than what we can actually see.
Yes, and if you did look in both directions and could see something 13 billion light years away, that way and that way, it stands to reason that from where you are, you're looking across 26 billion light years. Would that be correct?
Yes, but if
fundamentally.
Yeah. I mean, that's right, and that's the separation between them. In fact, we're talking a little bit enigmatically anyway, because the proper distance so if we have a look back time of 13.8 billion years to a baby galaxy, that is the distance that we see presented to our telescopes. But in reality, because the universe has been expanding since the light left it, that is probably more like 40 billion light years away. And that's something we call the proper distance. But there's no point in imagining the proper distance or thinking about it, because all the information comes at the speed of light. So yes, the universe is much bigger than we can see. But the distance is. I think it's always better to talk in terms of look back time rather than distances when you're looking towards the limits of look back time, which is the flash of the Big Bang.
Yeah. I'm going to ask AI how big the universe is.
See what it says.
Yeah.
How big's the universe? Oh, it's quite a big thing, Squire.
Well, they say the observable universe is approximately 93 billion light years in diameter.
Yes, okay. So that's exactly what I said. It's 40 odd light years to the proper distance of the horizon. But the proper distance takes into account the expansion. That doesn't matter to us, because all we can see is what we can measure in light years, look back time.
Yeah, it's fascinating and confusing all at the same time. Really, really interesting.
But the main word there in that AI answer is observable. That's the observable universe. That's all we can see. There's much more.
What we can't see is much, much bigger.
Much bigger.
We can't even put a number on that, can we?
No. Could be infinite.
No idea. All right, Tom, love your question. Thanks so much for bringing that up. It's always a good discussion point, and it just keeps you thinking. It does. So thanks to everyone who sent questions in, Andrea, Michael, George and Tom. And if you've got questions for us, please send them via our website. And you can do that through the Ask Me Anything button at the top, AMA, where you can leave text and audio questions. Don't forget to tell us who you are and where you're from. And Fred's about to find out who that is and where they're from. They're probably from the other end of the universe. Could be Hugh. Wouldn't that be a coup? Indeed. But thanks for your questions and keep them coming. And while you're on our website, have a look around. Maybe click on the support our podcast button and see if you can help us out. It's totally optional. And plenty of other things to see and do, including visit the Space Nuts shop and leave some reviews while you're at it. Fred, thanks so much. It's been a great pleasure. Lots of fun.
Thank you, Andrew. Some excellent questions there. Thanks to all our listeners.
Professor Brett Watson, astronomer at large. And thanks to Hugh in the studio, who couldn't be with us today because time stopped for him. And from me, Andrew Dunkley, thanks for your company. We'll see you on the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.